Hello? Welcome to the Science Lullaby channel. Tonight we'll drift to the quietest and strangest places in the cosmos. Regions where space bends, time slows, and most of our understanding of reality begins to dissolve. We'll explore this mystery. Black holes. Not just what they are, but what they might contain. Not just how they bend light, but how they warp the rules of the universe. What lies beyond their edges? Is there even a surface? If something falls in, is it lost forever? Starlight glows. Black holes wait in stillness. They don't shine. They don't speak. Yet they shape entire galaxies. They bend the sky, capture time itself. So tonight, we begin with one. What if gravity isn't a force at all, but something deeper, stranger, more fundamental? Before we understand black holes, we must understand gravity, not as a force but as a shape. This may sound strange, but this idea represents one of physics' greatest paradigm shifts. In the early 20th century, it began with Albert Einstein's insight that space and time are not separate entities, but parts of a unified fabric, a fabric that can bend. In Einstein's general theory of relativity, gravity isn't some mysterious long-range pull. It occurs when mass causes spacetime to curve. The motion of objects isn't guided by invisible forces, but by the shape of the space they traverse. Imagine placing a marble on a stretched sheet. If the sheet is flat, the marble stays where you placed it. But if you put a heavy object in the middle, the sheet sags. The marble rolls inward, not because something is pulling it, but because the surface beneath it is now sloped. Gravity in this view is a response to curvature. Earth doesn't fall toward the sun because it's being pulled. It follows the curve of space created by the sun's mass. The same principle applies everywhere, from planets orbiting stars to the most extreme cases at the center of black holes. When too much mass is squeezed into too little space, space-time doesn't just bend gently. It folds in on itself. At a certain threshold, the curvature becomes so steep, there's no turning back. Not even light can escape. That's the definition of a black hole. But it's not a hole in the sense of emptiness. It's a real region of space, physical and structured, where space-time's shape curves only inward. A black hole is not absence. It is a presence. Dense, curved, invisible. The boundary of this region is called the event horizon. It is not a surface in the usual sense. You cannot touch it, or bounce off it. It is not made of matter. It has no texture or temperature. But it marks a profound divide in the cosmos. Signals from outside can still escape. From inside they cannot. The horizon is the path of light. Everything else turns inward. Forever. It is the edge of visibility, the point of no return. If you float above the horizon, you can still send messages, just as distant stars remain reachable from your ship. But move 1 inch closer, and all paths forward lead deeper in. There is no outward direction left. Not because something blocks you, but because the shape of space itself no longer permits escape. The horizon is a point. Geometry overrides intent. Direction ceases to be a matter of choice. This boundary, though it sounds strange, is smooth. If you fall toward it, you won't feel it pass. No tremor. No flash. The curvature intense but not abrupt. For many black holes, especially the supermassive kind, the experience at the horizon may be almost gentle. From the outside, it looks like an invisible shell, but from the inside, a deeper silence, a future narrowed to a single destination. The event horizon won't destroy you. It simply removes you from the story. The rest of the universe can tell the difference. So what happens when something falls in? From afar, time appears to slow. A spacecraft drifting toward the event horizon seems to move ever slower. As it nears the edge, its light stretches outward, redshifting into invisibility. To a distant observer, the ship never crosses the line. It simply fades away. But from the ship's own perspective, the experience is profoundly different. Time flows normally. Instruments tick. Clocks count. The boundary crossed in an instant. Once over, the fall continues. Silently, inexorably. Within the horizon, there is no turning back. The future, defined by space-time structure, can only lead deeper. For the ship or the star or the signal, whatever it may be, further descending into the curved interior. But it does not collapse toward the center, in the way we usually imagine. It heads toward another kind of end. A place marked not by distance, but by the collapse of the rules themselves. This is what we call a singularity. Though the word is familiar, its meaning is stranger than we usually imagine. A singularity is not a thing. It is not a point in space. It is the failure of the map. A place where the equations of general relativity cease to work. According to the mathematics, the density of matter becomes infinite. The curvature of spacetime becomes unbounded. The paths of light and matter end, not because they hit something, but because they have nowhere to go. Time itself seems to lose meaning. Yet, this is not a physical object. It is the edge of our understanding, a region where known physical laws no longer apply. Some physicists believe singularities are real, that space and time truly end at a final point. Others see it as a placeholder, indicating our theories are incomplete. A deeper framework, perhaps incorporating quantum mechanics, must take over. Until we possess such a theory, the singularity remains an enigma, a place foretold by mathematics, yet invisible to all, always hidden behind the event horizon. It shapes the black hole from within, and we can never reach it. The singularity lies at the center of a classical black hole, but it is not part of the observable universe. No light can escape it. It sends no signals. We know it exists only through the behavior of the space around it. Orbits warped, time stretched. The way matter vanishes from view. The singularity is not what we see. That is why we see nothing. Its presence warps the rules, bending every path inward, until escape becomes not difficult, but impossible. In this sense, a black hole is not a hole at all. It is a space, enveloped in utter silence. The universe cannot see inside. What goes in does not return. What lies within cannot emerge. Yet, this is not destruction in the usual sense. Mass remains. Influence persists. Gravity still acts upon the outside world. A black hole possesses what it devours. Even if it cannot return it, it becomes a memory, sealed behind an impassable boundary. Conversely, from afar, a black hole appears unremarkable. It has no visible features, no glow, no outline, but its gravity, like any other massive object. Planets can orbit it. Light can bend around it. If you didn't know what lay at its center, you might mistake it for an exceptionally massive star. This is one of the most astonishing things about distant black holes. Their behavior appears almost normal. Only when you approach do peculiar effects emerge, where space's curvature steepens. Imagine replacing the Sun with a black hole of identical mass. Earth would continue orbiting as before. Light would vanish. Yet the gravitational pull would remain unchanged. This tells us something crucial. A black hole isn't special because its pull is stronger. It's special because it's so compact it squeezes into a smaller space. The curvature of spacetime becomes extreme only near the event horizon. Farther softens the geometry, and the rules of motion return to familiar patterns. What makes a black hole unique isn't gravity itself, but the structure it creates. A region of space where the normal path, the geodesic, forever curve inward. Time tilts toward a single outcome. A black hole doesn't suck things in like a vacuum. It simply offers no outward path. It warps the map so all roads lead downward. Once you're in, only these paths remain. The outward direction no longer exists. A common image is a black sphere or deep pit, but these pictures are misleading. Black holes have no surface. They possess no outer edge you can touch. The event horizon is not made of matter. It is a boundary defined by light and causality. If you were falling, you wouldn't collide with anything at the edge. You would pass through, unknowingly transitioning. The horizon is not a wall. It is a moment, a change in the shape of time. In this way, black holes are both real and intangible. They can collide with stars. They can grow by devouring matter. It can merge in orbit. It radiates gravitational waves. Yet, it possesses no tangible structure. Where it begins, the horizon isn't a location in space, but a feature of spacetime itself. The closer you look, the more abstract it becomes. Not a shell, not a crust, just a boundary, a place of no escape, an option. Even if the horizon is invisible, it is precise. It possesses a measurable dimension called the Schwarzschild radius. This radius depends solely on the black hole's mass. For the Sun, approximately 3 kilometers. For Earth, less than 2 centimeters. The greater the object's mass, the larger the radius. Yet the nature of the horizon remains unchanged. It is not a barrier. It is a place where all futures fall inward. Not a surface, but a void. Within the event horizon, space and time switch roles. Past becomes future. Inward collapse. Not merely a choice. Time itself. Each second draws you closer to the singularity. Not because you're being pulled, but because all paths through spacetime now converge in that direction. Just as we cannot halt time's advance, objects within a black hole cannot cease their descent. The internal geometry defines its own version of inevitability. This interior isn't merely empty. It possesses structure, even if we can never see it directly. Curvature steadily increases. tidal forces grow ever stronger. The separation between objects begins to stretch in one direction and squeeze in another. The farther you fall, the more extreme the environment becomes. Yet still, the experience is shaped by the same principle. Spacetime isn't flat. It folds inward. Every path through it narrows toward the core. This is the true black hole. There is no hole in the universe, but a region of space-time, completely inwardly curved, defined, not by what it is made of, but by how it bends what passes through it. This is a place where motion loses direction. Time becomes location. Gravity ceases to be merely a force. It is the shape of destiny itself. Outside, darkness is seen. Inside, a map is followed, leading to places we cannot reach. The simplest kind of black hole is one that does not spin, nor carry charge nor spin. It is a perfect, spherically static, and is defined by only one property: its mass. This type is called a Schwarzschild black hole, named after Karl Schwarzschild, who first solved Einstein's field equations for a non-rotating point mass. It is the cleanest, the most symmetrical version of a black hole. It is the starting point for understanding the rest of the universe. The Schwarzschild black hole has no hair, no extra features, no obvious characteristics. It looks identical from every angle. The space around it curves smoothly. The event horizon forms a perfect sphere. The size of this horizon depends entirely on the mass inside. There is no surface beneath it, no structure suspended in space. The geometry itself defines the boundary. Mass determines the radius defines the shape, and the shape, rearranged into a region where time and motion curve inward. No return. In the real universe, most black holes aren't perfectly stationary. They spin. This spin changes everything. The Kerr solution describes a spinning black hole, discovered by Roy Kerr in the early 1960s. Like the Schwarzschild solution, it precisely solves Einstein's equations, but not for a stationary sphere. It describes a rotating structure. The very fabric of spacetime is dragged into motion. This rotating geometric framework envelopes the black hole and alters the behavior of everything nearby. The faster the black hole spins, the more distorted this space becomes. The event horizon is no longer the sole boundary. Rotation introduces a second boundary, an outer region called the ergosphere. Here, the fabric of space is not merely curved but twisted. Any object within the sphere is forced to move, even if it could theoretically remain stationary. Not because it is pushed, but because the space around it is spinning. Even light must rotate with the flow. This peculiar effect is called frame dragging. It means space and time itself are dragged along by rotating mass. In ordinary physics, we consider space to be passive, a background. But in general relativity, space is active. It bends. It moves. Near a curved black hole, it rotates. An observer within the energy ring would find every direction contains a spin component. No point is stationary. Everything proceeds quietly and resolutely around the black hole's axis. The energy ring lies just beyond the event horizon. It touches it at the poles, but extends farther around the equator. Within this region, extraordinary things become possible. Particles entering the energy ring split. One part falls in, while the other escapes with greater energy than before. This is called the Penrose process, named after Roger Penrose, who proposed it in the 1970s. Theoretically, it allows energy to be extracted from a black hole's rotation without violating the rules. The energy gained comes from the spin itself, as the black hole slows slightly, while the escaping particle carries away the difference. Over time, this process could cause the black hole to lose angular momentum, gradually shedding its rotation. Though unlikely in natural settings, it reveals a profound truth about these objects. They are not entirely isolated. Under the right conditions, they can feed back, non-mass, and not light. But the spinning vortex is not a place we can go. Yet it is a region with measurable effects. Light near the edge is warped. Particle trajectories diverge. The very fabric of spacetime becomes dynamic. In this way, a spinning black hole is not merely a deeper version of stillness. This is qualitatively new. Vortexes and cosmic structures, gravity and motion fuse into geometry. This is both elegant and strange. The Penrose process is not merely a mathematical curiosity. It reveals something subtle about the relationship between motion and energy. In curved spacetime, when a particle enters the other world, its trajectory bends with the flow. If it splits into two, one fragment could be sent deeper into the black hole, while the other escapes. The trick lies in momentum conservation. The falling fragment carries negative energy from a distance, allowing the other to escape with more energy than it started with. This isn't free energy. It originates from the black hole's rotational energy itself. Over time, repeating such interactions gradually slows the rotation. The black hole's total mass remains unchanged, but its angular momentum diminishes. The process is inefficient in most astrophysical settings, yet theoretically sound. It demonstrates that even something as closed off as a black hole can interact with its surroundings, not by expelling matter, but by altering its properties. Stephen Hawking later expanded this concept, along with other ideas in black hole thermodynamics. A spinning black hole possesses not only mass, but angular momentum, surface area, and entropy. These quantities follow rules that closely resemble thermodynamic laws. In this context, the Penrose process becomes a form of energy conversion that violates no principles. Instead, it reveals that black holes may be governed by profound and universal laws that manage not only the laws of matter, but the very structure of space. Deep within a Kerr hole, the geometry grows stranger. Unlike a non-rotating black hole that terminates at a single point, the Kerr solution predicts something more complex. The singularity is not a point, but a ring, a rotating ring of infinite curvature. The precise meaning of this structure remains debated, but mathematically, it creates something extraordinary. A region of space that can be traversed. A hypothetical passage through the center. Theoretically, this ring's singularity opens the possibility of a wormhole, a tunnel, to another part of spacetime, Whether such a thing exists in reality is highly uncertain. The internal structure of spinning black holes is unstable. In most models, minor perturbations cause it to collapse or violently oscillate. Yet the mathematics suggests some kind of passage, not a doorway in the usual sense, but a path embedded within the very curve of space itself. If true, this implies black holes are not merely endpoints, but bridges. Falling into one might not mean destruction, but relocation. No evidence exists of this occurring in nature. Most physicists believe the internal structure is far more chaotic than these solutions suggest. Yet, the ring singularity remains a fascinating clue, offering a glimpse of what warped space might permit. Under extreme conditions, this indicates we still have much to learn about the shapes within. There exists another type of black hole, permitted by Einstein's equations, the charged variety, described by the Reissner-Nordström solution. It adds charge to a non-rotating black hole. Just as mass charge affects spacetime, it alters the shape of the curvature and introduces new boundaries. Charged black holes feature not one but two event horizons, an outer one, and an inner geometry that becomes more extreme. Increased charge alters the internal structure. Between these two horizons lies a region where time and space behave in stranger ways. If you were falling in, you'd first cross the outer horizon and lose contact with the outside world. But you wouldn't immediately hit the singularity. Instead, you'd pass through another horizon, beyond which the curvature becomes even stronger. The path continues inward, toward the singularity, in many ways similar to the one in Schwarzschild's case, but now shaped jointly by gravity and electromagnetism. In reality, black holes in nature are unlikely to carry large charges. Any significant imbalance would quickly attract opposing charges from the surrounding environment to neutralize the effect. But as a mathematical possibility, charged black holes are valuable. They demonstrate how general relativity accommodates not just mass, but other forms of fields and energy. They reveal new structures within the horizon, boundaries and interior regions that do not exist in uncharged cases. When both mass, spin, and charge are present, we obtain the most common black hole type, the classic general relativity Kerr-Newman black hole. It rotates, charges, and warps in all directions. Its geometry is the most complex. Its interior contains the richest set of possibilities. Like the simpler Guardian solution, it includes a ring singularity. Like the Reissner-Nordström black hole, it includes multiple event horizons. It also predicts regions of negative energy and complex paths through spacetime. These solutions are mathematically perfectly symmetric and eternal. Yet nature seldom offers perfect symmetry. True black holes form from collapsed stars, merging giants through chaotic processes. They seldom remain static. They ripple, sway, and settle. Still, these idealized models provide us with a map. They tell us what is possible, at least in theory. In doing so, they stretch our imagination, revealing geometries far beyond anything we experience in everyday life. The most abstract of these solutions suggest extraordinary things. black holes might be portals to other regions of spacetime, beyond the event horizon. The map might extend to wormholes and white hole tunnels. These are permitted, in principle, by the equations, but they come with conditions. Perfect symmetry, absolute stability, strange matter. To date, we have seen no evidence of these in nature, yet their mathematical existence challenges our understanding. They remind us that general relativity is not merely a theory of gravity, it is a theory of shape. Some shapes are stranger than any we have seen. Every black hole begins as something else. Most commonly, it is a star, a massive, luminous ball of gas, burning with the heat of fusion. For millions or billions of years, stars balance two opposing forces: gravity's inward pull and outward pressure from nuclear reactions. At its core, hydrogen fuses into helium. Energy escapes as light. This light prevents collapse. The result is equilibrium, a delicate, constant tension between contraction and expansion. The greater a star's mass, the fiercer the struggle. Gravity pulls harder. Temperatures soar. New layers ignite. Helium becomes carbon. Carbon becomes oxygen. This process builds inward and upward, creating fused shells like onion layers. Each new stage produces heavier elements. But pressure always depends on heat, and that heat comes from fusion. As reactions continue, stars survive. When they end, the balance breaks. At the end of a massive star's life, iron appears at the core. This marks a turning point. Iron cannot fuse into heavier elements. It doesn't consume energy. Instead, it releases it. The chain reaction halts. The furnace cools. And without fusion pressure to counteract immense gravity, the core begins to collapse. Collapse occurs within seconds, setting the stage for one of the universe's most dramatic transformations. As the core shrinks, outer layers collapse inward. Pressure exceeds the limits of ordinary matter. Electrons are compressed into protons, forming neutrons. Neutrinos flood outward. The shockwave rebounds, tearing through the falling gas. If conditions are right, this shockwave becomes a supernova, an explosion that could outshine the entire Milky Way. Outer layers are hurled into space, but the core, now incredibly dense, remains behind. What it becomes depends entirely on its mass. If the remnant is small enough, it may stabilize as a white dwarf or neutron star. These are peculiar objects themselves, supported by quantum pressure, the degeneracy effect, arising from the regularity of high-density particles. But if the mass is too great, even this exotic pressure cannot withstand gravity. There is a limit, known as the Thomson-Oppenheimer-Volkov limit. Beyond it, no known form of matter can resist collapse. When this threshold is surpassed, the outcome is inevitable. Gravity overwhelms all. The core compresses beyond neutron star density. No known force can halt it. Curvature steepens. The surface vanishes. A black hole is born, not through violent explosion but through final inward collapse. When geometry folds completely upon itself, what remains is not remnants of matter, but an inescapable region of spacetime. The end of a star marks the beginning of something new. when equilibrium is shattered within a massive star. Collapse does not begin at the surface, but deep within the core. The once fiery, stable innermost region yields to gravity. Initially, contraction proceeds slowly, resisted by the quantum pressure of electrons. But as density increases, electrons are forced into higher and more energetic states, until they begin combining with protons to form neutrons. This alters the very nature of matter, removing the final barrier against collapse. The core suddenly becomes opaque to its own light. Heat and pressure surge rapidly, but before they can be released, the structure tightens further. At this stage, density rivals that of atomic nuclei. Something like 100 trillion grams per cubic centimeter. Time slows. The filling accelerates then. Briefly, the inward motion halts. Rebound begins. This rebound is the shockwave that begins to explode outward. The first spark of a supernova. Yet shock alone is not always sufficient to trigger an explosion. Most energy is absorbed or stagnates within surrounding layers. What can save the process, at least in some models, is a torrent of neutrinos. These ghostly particles, created in vast quantities during collapse, flow outward at near light speeds. Despite their weak interaction with matter, at such extreme densities, even a tiny fraction absorbed can reignite the shockwave. When this occurs, the outer layers are torn away in a blinding pulse. The result is a core collapsing supernova. A star, undergoing such violent transformation, rivals the brightness of entire galaxies. This is where heavy elements are forged. Gold, everything beyond uranium and iron. At that moment, the star returns its contents to the cosmos. Yet within its core lies something denser still. Whether it becomes a neutron star or a black hole depends not on the explosion, but on what remains. A mass-determined threshold governs this outcome. If the core is less than, roughly 2 to 3 times the Sun's mass, it may stabilize as a neutron star. Such a dense object weighs more than a mountain in a teaspoon. It does not sustain itself through fusion, but through neutron degeneracy pressure, quantum resistance to further compression. These are stable, long-lived remnants, spinning and glowing, sometimes pulsing across the sky like cosmic lighthouses. But if mass exceeds the limit, degenerate pressure fails. Gravity crosses a point of no return. Instead of a solid remnant, the core continues collapsing, plunging inward, through its own event horizon. No light escapes. No surface remains. A horizon forms around it. From that point on, a black hole exists not as an object in space, but as a region of space. The past ends in silence. The formation is complete. The star is gone, but its gravity remains. Neutron stars are among the strangest stable objects in the universe. They form from the collapsing cores of massive stars that nearly became a black hole. At this point, matter is compressed so tightly that protons and electrons merge into neutrons. These neutrons form a superdense fluid, no longer composed of atoms, but of nuclear matter, packed into a state beyond anything in ordinary physics. It is not solid, not gaseous, not even plasma. It is something else, constructed solely by quantum rules. The force supporting this object is called degenerate pressure, a quantum mechanical effect, emerging from the exclusion principle, which states that no two identical fermions, like electrons or neutrons, can occupy the same quantum state. As the core compresses, neutrons are squeezed into fewer possible states, until the resistance from this rule becomes strong enough to halt further collapse. The result is a star, only 10 to 15 kilometers in diameter, yet denser than the Sun. At the surface of a neutron star, gravity is billions of times stronger than on Earth. The crust is only a few centimeters thick. Beneath it lies a dense mass of neutrons, spinning, bending, and vibrating at strange rhythms. Some neutron stars rotate hundreds of times per second. Others emit beams of radiation, sweeping across the sky like cosmic lighthouses. These are pulsars. They are precisely stable and profoundly mysterious, but they are not bulletproof. If enough matter is added, their structure collapses. Beyond this limit, the neutron star can no longer support itself. This is known as the Tolman-Oppenheimer-Volkov limit, or TOV limit for short. It corresponds to the neutron star's Chandrasekhar limit, the white dwarf's Sika limit. When the precise value depends on details of nuclear physics, still under investigation, generally estimated around 2 to 3. Beyond this solar mass threshold, neutron degeneracy pressure becomes insufficient. Gravity takes over. No known state of matter can halt the collapse. The TOV limit marks the boundary between the visible and the hidden. Below it, we observe neutron stars, observable, compact, sometimes even predictable. Above it, we enter the realm of black holes. Once crossed, the structure cannot stabilize. No internal force can resist. The collapse continues, not into a new star, but into a new region, where the rules of motion and space offer no escape. This is the threshold, the vanishing point. This limit also hints at the mysteries of dense matter. We don't fully understand what happens inside neutron stars. Some theories suggest the core may dissolve into quark matter, a denser state, where individual neutrons split into their constituent particles. Others speculate about hyperon, meson condensates, or strange matter. In principle, any of these could raise or lower the TOV limit. But until we can observe these interiors more directly, the post-hole remains the ultimate answer. When mass crosses this line, when the collapsing core of a massive star exceeds the TOV limit, no known force can halt it. Neither neutron pressure, tension from the nuclear force, or even the resistance of quark matter. None suffices. Gravity warps space sharply. No stable configuration exists. Things continue inward, accelerating forward. Time, from the outside, slows at the edge. But for the matter itself, the plunge continues rapidly, unstoppable. The collapse does not explode. It does not freeze. It passes a point of no return and presses on. From the outside, the event horizon forms a spherical boundary, where escape velocity reaches light speed. Within this boundary, space continues to fold, guiding all paths toward the singularity. The core no longer exists as matter in space. It has become part of a new geometry. A region, not a thing. A shape from which light cannot escape. This moment marks the true birth of the black hole. Not as a leftover object, but as a transformation of spacetime itself. The gravitational field persists. Mass remains, but there is no longer a surface. No longer a place to point at. This is the star. A black hole is no longer made of matter. It is made of the space that once surrounded it. Reconfigured, sealed, and redefined. The star is gone, but its presence endures in the warp it leaves behind. The size of a black hole does not remain constant. They can grow. One of the primary ways they grow is by eating. When gas, dust, or even stars drift too close, they may fall in. Not all at once, but gradually, spiraling inward through a structure called an accretion disk. This disk is flat, rotating, often extremely hot. Interlayer friction heats the material and radiates energy, sometimes enough to outshine entire galaxies. The process is messy. As matter falls toward the black hole, it loses angular momentum and energy. Magnetic fields twist. Plasma flares. Turbulence churns the disk into luminous storms. The closer matter gets to the event horizon, the faster it moves. Some fall in, others escape via jets, exploding out along the poles at near light speeds. These jets don't originate from inside the black hole, but from the outer regions of the disk, launched by magnetic forces and rotation. Despite the violence, the process is highly efficient. Black holes can convert most of the falling material, mass, into energy before swallowing it whole. This makes accretion one of the brightest engines in the cosmos. In some cases, black holes power quasars, supermassive beacons spanning cosmic distances. These feeding frenzies can last millions of years, transforming quiet galaxies into active ones. Black holes remain hidden, but the feast leaves vivid traces. Some of the clearest evidence for black holes does not come from solitary giants, but from those in pairs. Black holes in binary systems orbit companion stars. In these systems, material from the star spills toward the black hole, pulled down by tidal forces, and enters an accretion disk. The falling gas heats up and radiates intense energy, especially in the form of X-rays. These high-energy emissions can be detected from Earth, revealing the existence of something immense, compact and invisible. Unlike ordinary stars, these dense objects do not shine on their own, but their fingerprints are unmistakable. The way they move, the way they bend light, and the energy released by surrounding disks, all point to their true nature. Some of the earliest black hole candidates, like Cygnus X1, were discovered this way. Visible stars, orbiting dark objects, large enough to be black holes. These systems offer a unique window into black hole growth. When two black holes orbit each other, the system becomes even more intriguing. Over time, they spiral closer together, radiating energy in the form of gravitational waves, ripples in space-time itself. These waves carry away momentum, causing the orbit to shrink. Eventually, the black holes merge in a violent collision, sending out a final exam. powerful waves sweeping across the cosmos. These events are rare, but they can now be observed directly. The first detection of gravitational waves came in 2015 from two merging black holes, over 1 billion light-years away. The signal lasted less than a second, but its mass equaled several suns. It confirmed predictions of general relativity, formulated 100 years prior, unlocking a new astronomy. Without light, yet with the stretching and squeezing of space itself, each merger we detect reveals mass, spin, and distance. About how black holes meet and grow. These gravitational waves are not merely violent echoes, but records of geometric motion. They tell us black holes are not silent, but sing in a language of curvature and rhythm. As they collide, the final remnant is larger than either original black hole, yet lighter than their combined mass. Some energy radiates away as waves, leaving behind a new, heavier, spinning black hole. These mergers contribute to the cosmic population of black holes. They help seed larger structures over billions of years, colliding and growing. Black holes amplify from stellar remnants into more massive entities. They become the gravitational cores of galaxies, not through sudden creation, but through a long process of accumulation. Their growth involves not only devouring stars, but also merging with each other, weaving the deep geometry of space between stellar black holes, born from dying stars, and the giants at galactic centers, lies a mysterious realm of intermediate mass black holes. These are objects ranging in mass from hundreds to hundreds of thousands of times the mass of the Sun. For decades, their existence remained uncertain, too massive to form from a single star, yet too light to rival the giants we observe in galaxies. They occupied a liminal space, missing links between known extremes. Signs of their presence began emerging in dense star clusters, where the motion of stars within these ancient spheres suggested the influence of hidden mass contracts larger than any single star. X-ray emissions from superluminal sources also point to the accumulation of something heavier than stellar black holes, yet not massive enough to be considered supermassive. These may be the long-sought intermediates, slowly revealing themselves in the quiet corners of the cosmos. How they formed remains an open question. One possibility involves violent collisions within young clusters, where massive stars merge before exploding. Another pathway may involve gradual mass accumulation through accretion and mergers, bridging the gap between stellar and galactic scales. Whatever the origin of intermediate mass black holes, seeds, precursors, for giants, we now observe anchoring galaxies in the sky. Supermassive black holes are the largest known, residing at the centers of galaxies, including our own Milky Way. These giants range from millions to billions of solar masses. Yet, despite their immense size, their gravitational pull tapers gently at the event horizon. One might fall in, without even noticing crossing the edge. The curvature of space is gradual, extending over vast regions. These are not densely packed in the traditional sense. They are large, yes, but spread across a vast, quiet sphere. How these monsters formed remains one of astrophysics' greatest mysteries. Some may have grown slowly over billions of years. Gas and dust supply, and merging stars. Others may have formed rapidly in the early universe, from the direct collapse of primordial clouds. Quasar observations, ancient beacons of brilliance, indicate some supermassive black holes were already in place, less than a billion years after the Big Bang. Their growth rates challenge many models and invite new ones. What is clear is that supermassive black holes are not passive residents at the center of galaxies. They shape their environments. Their gravity controls stellar motion. Their radiation influences gas flows. They regulate star formation and impact the structure of galaxies themselves. In some cases, they launch jets, spanning hundreds of thousands of light years. These are not mere endpoints. They are engines. Their role in cosmic evolution is profound. Around many black holes, especially massive ones, a luminous storm of matter called an accretion disk spins. This disk forms as gas and dust spiral inward, under gravitational pull, but are slowed by friction and angular momentum. As particles rub against each other, they heat up. Temperatures soar to millions of degrees, and the inner regions of the disk glow with X-rays and ultraviolet light, though the black hole itself remains invisible. The disk emits astonishing brilliance. These disks are not merely luminous. They are dynamic. They twist and ripple. Magnetic arcs and reconnection. Turbulence creates vortices and waves. Sometimes, even more wondrous things occur. The black hole emits jets. These narrow beams of particles and radiation shoot out from the disk's poles, traveling at speeds approaching light. They extend far beyond the galaxy, piercing interstellar space with a focused stream of energy. The exact mechanisms behind these jets remain under study, but magnetic fields likely play a central role. As the rotating disk warps the field, it creates coils that channel energy outward. The black hole's own spin may also contribute, extracting angular momentum and converting it into kinetic energy. Regardless of the process, the result is one of the most powerful events in the universe. A silent object emits a roar of light and motion, spanning millions of light years. These effects are not confined to the black hole. The surrounding environment, the energy released through accretion and jets, can reshape entire galaxies. It can heat gas, suppress star formation, and carve voids in the interstellar medium. This is called feedback. It plays a crucial role in regulating galactic growth. Without it, galaxies might grow too rapidly or form stars too freely. The black hole, small compared to the galaxy, acts as a governor in its evolution. This feedback operates largely through a single supermassive black hole, whose radiation and jets influence stellar behavior hundreds of thousands of light years away. It can constrain cooling, dispersing clouds, and drive winds sweeping across the galactic halo. Observations of elliptical galaxies often reveal signs of this. Giant bubble shock fronts and filamentary structures formed by past outbursts. These are not random accidents. They are signs of the central engine at work. In this way, black holes are not mere endpoints. They are the sculptors of structure. Their influence begins small in the warping of disks or the launch of jets, and extends outward into the architecture of space itself. They grow by feeding, but in turn, they guide the flow of matter and energy from the galaxy's center. Silently, they sculpt the universe's form on two scales, intimate and immense. The edge of a black hole bears no material markings or structures. It is marked by time. From afar, objects falling toward a black hole appear to slow down. As they approach the event horizon, their motion becomes sluggish. Their signals stretch. This is not a visual trick. It is the fundamental effect of warped spacetime. Gravity alters the flow of time. Near the horizon, time stretches toward infinity. The closer you get, the slower time flows, at least as seen from afar. This deceleration isn't experienced by the falling object. Its own time continues smoothly. 10 seconds pass. Instruments read normally. But for a distant observer, these moments unfold over hours, years, centuries. The object appears never to cross the horizon. It hovers. Descent freezes. Its image vanishes, yet never disappears. In truth, it does fall. But the light it emits becomes so stretched, so delayed, that the final moment never arrives. This peculiar behavior is Einstein's expression of equivalence between gravity and time. Clocks tick slower in strong gravitational fields. Near Earth's surface, this effect is minuscule, a few billionths of a second per year. But near a black hole, it becomes dramatic. The time difference between the event horizon and infinity can be essentially infinite. Looking down that well is looking into the future. Falling in is leaving one timeline and entering another. The time dilation is related to a second effect: gravitational redshift. As light crawls out of the gravitational field, it loses energy. But light cannot slow down, so its wavelength stretches. It shifts toward the red end of the spectrum. The stronger the gravity, the greater the shift. Near the event horizon, the effect becomes extreme. Even visible light redshifts into infrared, then microwaves, and finally radio waves. It becomes completely undetectable. This redshift isn't caused by motion, like the Doppler effect. It stems from the geometry of space itself. The light source hasn't changed. It merely crawls across a warped landscape, and that climb stretches it. For a falling object, this means any signal it emits grows ever fainter, longer and more delayed. To a distant observer, it seems to vanish, not to stop, but to fade away over time. Its final moments smeared across the ages. These two effects, time dilation and redshift, define the edge of a black hole. They tell us the end of the visible world. No wall, not with flames, but with a deepening silence. The event horizon is not a barrier. It is a boundary where light grows endlessly weary. Time slows endlessly. Nothing dramatic happens at the threshold. But once crossed, the path back vanishes. Light fades. Clocks slow. The view outside disappears without a trace. Falling into a black hole from afar seems infinite. Objects appear to hover forever, just above the event horizon. Their image dims and reddens, until they vanish from view. But from the perspective of the falling object, this is not what happens at all. It moves forward through time as usual. The horizon approaches, passes behind it, and recedes. No pause, no freeze. Not a moment's delay. Just downward motion. Smooth inward flow. These two views don't conflict. They are both correct, within their own reference frames. This is one of the deepest insights of general relativity. Different observers can describe the same event in vastly different ways. Both may be right. To the autumn heavens, stretching into eternity, filling the traveler, it is finite. Contradictions vanish. When we understand time itself is not absolute. It bends with gravity. At the edge of a black hole, it bends completely. To resolve this discrepancy, physicists employ two coordinated times, proper time and universal time. Universal time is measured by distant observers, far from the black hole. Where spacetime is flat, clocks run uniformly. This is the time marked by telescopes and detectors, satellites, and sensors. Proper time is the time experienced by a clock. On its own, it is not shared by the local individual. This is the time on your watch, ticking away through the world. When gravity is weaker, these two measures align. But near a black hole, they diverge. Coordinate time slows near the event horizon, reaching infinity at the threshold. Yet proper time remains finite. A person falling in might experience the entire descent in mere seconds or minutes of proper time, while to the outside world, the same fall seems to take forever. The falling object doesn't know it's stretching its own clock to tell a coherent story. This distinction isn't merely theoretical. It's crucial for understanding how black holes interact with the rest of the universe. From one perspective, it looks like a slow freeze. From another, a rapid plunge. Signal light and energy behave differently, depending on the perspective you adopt. This is why astrophysical black holes, though hidden, can still influence galaxies. Things falling inside seem to linger at the edge, glowing, burning, fading. Yet, as far as the event itself is concerned, the journey has already ended. At the core of it all lies a subtle. Spacetime is not the stage. It is the actor. It determines what can happen and how it unfolds. Falling into a black hole is not merely spatial motion. It is the reshaping of time itself. One observer sees delay. Another feels disagreement. Between them lies the event horizon, a boundary that does not halt time, but bends it so far, it no longer connects the two. For inward falling objects, the event horizon is not a wall. It is neither sharp nor abrupt. It has no surface, no impact. It is unseen and unfelt. No markers, no lights. No markers, but once crossed, it changes everything. From the outside, objects never fully reach this threshold. But from the inside, the crossing proceeds smoothly, unnoticed at first, irreversibly forever. The horizon is a boundary in the geometry of causality. Beyond this point, all possible paths lead inward. Crossing the event horizon is entering a space-time where roles are reversed. Outside the black hole, you move freely through space. Time carries you forward. Inside, it's the opposite. Space becomes the direction you cannot avoid. You move inward not by choice, but because every possible motion points that way. Every frame has a center. Even if you try to resist and turn around, there's no direction to escape. The moment of crossing can be quiet. A freely falling spacecraft might feel nothing. No tidal forces, no sudden pull. Especially if the black hole is supermassive. The curvature at the edge is gentle. Yet crossing it, absolutely no signal can leave. Nothing can be reversed. The rest of the universe becomes one thing. You can remember, but never reach again. The black hole doesn't suck you in. Simply, the road ahead in every path leads inward. Now, the horizon is where light is trapped. Photons emitted outward from the edge still travel at light speed, but they are carried inward by the shape of spacetime, like a swimmer against currents stronger than any stroke. They make no progress. From the outside, light emitted from the edge is infinitely stretched, redshifted into invisibility. From the inside, light still exists, but it cannot return. The horizon is a one-way surface, not for motion, but for information. This elevates the horizon beyond mere location. It is a boundary of causality, a surface dividing events into two realms, those that can influence the external universe, and those that cannot. It is not a solid object, but a constraint on possibility. From the outside, we see things falling toward it, but we never see anything cross over. From within, you can pass through it unnoticed, but you cannot traverse back. The asymmetry is not physical, but geometric. To truly grasp the horizon, we must abandon the notion of space as a container, or that action is always reversible. The event horizon is the edge of return. Once crossed, all timelines point inward. Not because anything propels you, but because the structure of reality itself shifts. The horizon is not a trap. It is a turning point on the map. And beyond it lies a region where even the meaning of direction begins to vanish. In Relativity, the concept of the light cone helps us understand what is possible. At every point in space-time, the light cone shows the direction light can propagate. From there, forward, outward, anything within the cone can reach it through signals, or move any unaffected external object. As you traverse curved space, the light cone tilts, bends, and shifts in response to gravity. Near a black hole, it begins to tilt inward. At the event horizon, it tilts completely. At the precise location of the horizon, the future light cone no longer includes direction. That point lies far from the black hole. All future paths, even lights, now guides inward. This does not mean light slows down. It still travels at the speed of light. But the shape of the space it traverses has changed. Its possible paths no longer exist. Every beam curves inward, carried by the warped spacetime toward the singularity. This shift marks a fundamental transformation. The tilting of the light cone is not merely a geometric curiosity. It signifies that the structure of causality has shifted. Beyond the black hole, no future exists. Not for anything crossing the horizon. All timelines converge inward. The center is not where you go. It is your moment of future. Inevitable certainty and silence. Once the light cone rotates, the rest of the universe exists only in memory. Once matter falls into the black hole, its individual characteristics seem to vanish. Atomic and molecular structures all disappear beyond the event horizon. What remains from the outside can be described by three things: mass, spin, and charge. These are the only measurable features. The black hole seems to retain all other details: the star's composition, the shape of its folded layers. Its history of motion is lost. This is the essence of Noether's theorem. The name is informal, but the idea is precise. Black holes have no hair, no surface features, no personality. They are defined by a few global parameters. Otherwise, they are smooth. The matter that falls in may be complex, but the black hole it forms is not. Two black holes of equal mass cannot be distinguished by spin or charge, no matter how different they were born. From the outside, they are identical. This raises profound questions. If a complex system collapses into a black hole, all its details vanish beyond the event horizon. Where does this information go? Is it destroyed? Is it hidden? Or is it somehow encoded in the geometry of spacetime? No information theorem states that black holes forget, but quantum mechanics shows information cannot be destroyed. This tension between the two principles leads us to one of modern physics' greatest mysteries: the information paradox. It begins with a contradiction between two of physics' most profound principles. On one side is general relativity, which tells us once matter falls into a black hole, its details are lost, leaving only mass, charge, and spin. Everything else vanishes beyond the event horizon. On the other side stands quantum mechanics. It insists information is never destroyed, even as particles scatter, merge, or transform. The total information about their state must, in principle, be conserved. This paradox becomes acute when we consider black hole evaporation. If a black hole truly forgets what it was made of, and then slowly vanishes through some natural process, the information it once contained would seem to vanish as well. Lays the foundation for everything that follows. Despite its simplicity, this solution is profound. It shows black holes are not strange anomalies, but the natural outcome of Einstein's theory. You don't need bizarre physics to create one. You only need enough mass in sufficiently small space. Compress dirt into marble. Compress the sun into a city. Theory handles the rest. The result is not a strange object sitting in space. It is space itself. This violates quantum theory. Not just a minor inconsistency, but a fundamental collapse. So physicists began asking, do black holes truly forget? Or is information stored somehow? We haven't figured it out. This question remained unresolved for decades, until radical ideas emerged in the 1970s. Stephen Hawking showed black holes aren't perfectly black. Through quantum fluctuations in empty space, black holes emit radiation. This phenomenon, now called Hawking radiation, revealed that black holes possess temperature. Thus they can evaporate slowly over unimaginable timescales, losing mass by releasing faint particles of light. Hawking's calculations built upon quantum field theory in curved spacetime near the event horizon. Virtual particle pairs constantly appear and annihilate. Occasionally, one falls into the black hole, while the other escapes. The escaping particle materializes, carrying energy away. Over time, this process diminishes the black hole's mass, until it may eventually vanish entirely. But if the radiation carries no information, if it is pure thermal radiation, then the information paradox only deepens. This radiation does not emerge from within the black hole, but originates near the horizon, shaped by the quantum properties of the vacuum space itself. The sky is a bit chilly, almost impossible to detect for stellar black holes, but its implications are profound. If black holes can evaporate, they are not eternal. If they emit radiation, they must possess entropy. If they vanish, the question becomes, what happens to everything they swallowed? Hawking initially argued information was lost. Black hole evaporation destroyed it forever. But many physicists disagreed. Over the years, new ideas emerged. Some propose information is cleverly encoded within the radiation. Others suggest the event horizon might store holographic imprints of everything. Still others speculate black holes don't entirely destroy information, but our understanding of space and time is too limited to see where it goes, to grasp information in black hole evaporation. Physicist Don Page proposed a simple: if a black hole emits Hawking radiation, if the radiation carries no information, then the entropy of the radiation should steadily increase as the black hole shrinks. But if information is somehow preserved and released over time, the entropy curve must bend. It should rise first, then fall. Like a mountain. This is the famous Page curve. In the early stages of evaporation, the emitted radiation appears hot, random, unstructured, and information-free. But if unification holds, if quantum information is conserved, this cannot persist indefinitely. Beyond a certain point, called Page time, the radiation must begin carrying information about the black hole's interior, reaching an entropy peak, then decreasing, until it reaches zero when the black hole fully evaporates. The once hidden information must return in the light. This poses a challenge to Hawking's original calculations, which predicted no such return. But recent advances, especially string theory, quantum information, and holography, suggest Page's curve might be correct. Techniques borrowed from entanglement entropy reveal how quantum gravity encodes surface information, not volume. These hints point to a deeper unification between spacetime and information, one that could reconcile the ghost of black holes with the laws of quantum theory. But to be certain, we must understand the center of a black hole, the singularity. In classical general relativity, a singularity is a point of infinite curvature, where density and gravity become undefined. It's not merely an extreme location. It's where the theory itself breaks down. Equations fail. Predictions vanish. Yet singularities lie in the future of every massive object. If we want a complete picture, we must go there too. This is where quantum gravity becomes crucial. General relativity cannot handle singularities alone. The theory assumes space-time is smooth and continuous geometry. But quantum mechanics states The world is composed of discrete wave units, somewhere near the Planck scale, where distances measure in trillionths of a centimeter. These two pictures must meet. At that meeting point, where singularities may dissolve, many candidate theories of quantum gravity, string theory, loop quantum gravity, causal sets, emergent spacetime, each offers distinct smoothing tools to eliminate singularities. Some propose spacetime isn't fundamental at all, but emerges from deeper quantum structures. Others suggest information resides within entanglement itself. Still others envision a black hole's core, not as a singularity but a rebound, a potential starting point for new universes. In seeking black holes' true nature, physicists venture into uncharted and the realms of the uncanny, ideas that seem closer to science fiction, yet emerge naturally from the equations. One such concept is the wormhole, a passage through space-time, potentially linking two black holes or two distant regions of the universe. If such structures exist, they might offer a path through a black hole, rather than a dead end. But most solutions allowing traversable wormholes require exotic matter or unstable conditions to be temporary. They remain mathematical possibilities. Another idea almost opposite to black holes is the white hole. Black holes allow nothing to escape white holes, allow nothing to enter. They are time-reversed collapses, explosions instead of implosions. Theoretically, information entering a black hole might emerge from a white hole elsewhere. Some speculative models suggest black holes could evaporate into a white hole phase, releasing stored information in a final burst. But white holes have never been observed. Then there are firewall models, proposed as solutions to the information paradox. The firewall hypothesis suggests the event horizon may not be smooth and empty, as predicted by general relativity, but instead teeming with activity. If information is encoded in Hawking radiation, then something must be broken, either universality or the equivalence principle, or nothing special occurs at the horizon. Firewalls would be walls of high-energy particles, burning anything that crosses them. But this view remains highly controversial. All these models, wormholes, white holes, firewalls, attempt to answer one question: how does information escape? If it doesn't escape, then quantum theory must yield. If it does, then our understanding of space-time must change. And increasingly, physicists realize the answer may lie in irrelevance, but in entanglement, invisible threads, binding quantum systems together. Entanglement isn't merely a particle property. It may be the scaffolding of space-time itself. Some researchers now propose space's smooth geometry emerges from entanglement patterns, just as holograms form from correlations. Under this view, a black hole's interior isn't a hidden place, but a construction of quantum relationships. When information escapes through radiation, it does so via shifting patterns of these connections. This idea leads to a startling possibility that space and time are not fundamental components of reality, but side effects of quantum information. If so, then the edge of a black hole is not the end of understanding, but merely the beginning of something deeper, a place where known rules give way. not to chaos, but to a structure we have yet to fully uncover, where physics begins to whisper the language of its own origin. So now, we are here. This journey has carried us through warped gravity, collapsing stars, and invisible thresholds. We linger at the edge of light, gently sliding inward, beyond the horizon not of matter, but of time. Perhaps in the quiet space, where science falls silent, thought begins to let go. Now there's no need to remember details. Equations can wait. Paradoxes may rest. What remains is the shape of thought. A vast, curved sensation. Calm and inevitable. Non-material existence. Yet gravity. Alone. Where time folds inward. Even light must bow to darkness. Out there, amid drifting galaxies, black holes wait silently. Some ancient giants, sitting like slumbering gods at galactic cores. Others are small and hidden, flickering in the shadows between stars. They do not seek. They do not chase. They simply are. Their existence is not defined by what they possess. Yet they will not let go. Perhaps in some way, the quiet of a black hole is no different from the stillness of a sleeping mind. Both slip beneath the surface. Both let the world fade. Both surrender to something slower, unfathomable. Not an endpoint, but a realm where thought cannot return. You needn't follow anymore. If you drifted away, that's just fine. If your thoughts have wandered, welcome them to stay wherever they may. If your eyes closed, let them rest a little longer. If you happen to be awake, listen softly at the edge of sleep. We'd love to hear your thoughts. What surprised you in this video? Did you learn something new? Feel free to share in the comments. If you seek a quieter journey, you're always welcome to subscribe. Because the story continues. It always does. In every atom of each orbit, in every quiet curve of space. We may never see the center. We may never know the edge. But we are part of the shape. All the same. Beneath the tranquil stars. The story continues. I hope you sleep well and dream gently. Good night. A star's destiny is sealed at its birth. Mass is the key factor determining a star's lifespan. A star functions like a cosmic nuclear fusion reactor. In its deep core, intense element synthesis occurs. Fusing hydrogen atoms into helium releases immense energy. This energy generates outward pressure, balancing the inward gravitational pull from the star's own mass. Achieves a delicate equilibrium. This balance sustains the star's stable existence, allowing it to shine continuously in the cosmos. For millions, even billions of years. For medium-mass stars like our Sun, when the core's hydrogen fuel is exhausted, gravity begins to prevail. The core starts to contract under its own weight, causing temperature and pressure to surge dramatically. This ignites hydrogen burning in the outer core layers, while the core's extreme heat triggers helium fusion. This process causes the star's outer layers to swell dramatically, forming a red giant. Eventually, the star's outer layers are ejected into space, forming a beautiful planetary nebula, while the core collapses into a white dwarf, a dense object sustained by electron degeneracy pressure. However, for massive stars exceeding 8 times the Sun's mass, their fate becomes far more dramatic. The interiors of these stars function like cosmic alchemical furnaces. where heavier elements are produced layer by layer through nuclear fusion. Hydrogen fuses into helium. Helium fuses into carbon. Carbon fuses into oxygen. This process continues until iron is formed. Iron marks the endpoint of stellar fusion, because fusing iron requires absorbing energy, rather than releasing it. At this moment, the star's destiny undergoes a fundamental shift. When the stellar core accumulates sufficient iron, the fusion engine that sustained it for millions of years abruptly shuts down, deprived of outward radiation pressure support. Gravity, its eternal adversary, seizes absolute dominance. The core begins catastrophic collapse under its own immense weight. This process unfolds with astonishing speed. Within less than a second, the core collapses from thousands of kilometers in diameter to mere tens of kilometers. Density surges to atomic nucleus levels, exceeding 100 million tons per cubic centimeter. Under these extreme conditions, electrons are crushed into atomic nuclei by immense pressure, combining with protons to form neutrons, while releasing vast quantities of neutrinos. These ghostly particles escape at near light speeds, carrying away the immense energy of the core's collapse. The core now transforms into a neutron star, a peculiar celestial body supported by neutron degeneracy pressure. If the collapsing core's mass exceeds the neutron star limit of roughly 3 solar masses, known as the Tolman-Oppenheimer-Volkov limit, even neutron degenerate pressure cannot withstand gravity's relentless squeeze. No known physical force can halt this collapse. The core continues inward collapse through its own Schwarzschild radius. At this critical radius, escape velocity reaches the speed of light. The curvature of spacetime becomes infinitely steep. An event horizon silently forms. A black hole is born. This process is often accompanied by a supernova explosion. The star's outer layers are ejected at 1/10 the speed of light. The energy released in mere weeks may exceed the total energy emitted by the Sun over its entire lifetime. This cosmic-scale explosion is so luminous that it can briefly outshine an entire galaxy. Among the ejected material are the heavy elements forged through nuclear fusion over the star's lifetime. These elements later become the raw materials for a new generation of stars and planets. Even the carbon, oxygen, and iron essential for life originate from the deaths of these ancient stars. The formation of a black hole is not the end of the universe, but a transformation. The star's mass and energy persist in the cosmos in another form. Through gravity, they warp the surrounding spacetime. Some black holes grow by accreting nearby matter, while others merge with their counterparts to form even larger entities. These cosmic gravitational behemoths, though invisible themselves, shape the structure and evolution of galaxies. With their immense gravitational pull at the heart of galaxies, supermassive black holes act as cosmic regulators. Their presence and activity dictate the fate of entire galactic systems, from the birth of stars to their demise, from the formation of black holes to their evolution. Everything in the cosmos operates under gravity's dominion, following predetermined physical laws. Throughout this process, gravity remains the ultimate victor, determining the formation and evolution of cosmic structures. The event horizon is the most iconic feature of a black hole. It defines the visible boundary of a black hole. Within this boundary, escape velocity exceeds the universe's ultimate speed, the speed of light. This means any object, even light itself, once crossing this invisible boundary, permanently loses the chance to return to the external universe. The event horizon is not a physical surface. You cannot touch it with your hand, nor directly detect its existence with any instrument. It is more akin to a critical point in spacetime, a dividing line of causality. Mathematically, the event horizon is defined as the set of spacetime points where all outgoing light cones point inward. Though abstract, this definition precisely captures its essential nature. From an external observer's perspective, the event horizon exhibits perplexing properties. As an object approaches the event horizon, a pronounced time dilation effect occurs. The object's motion appears to slow progressively, until it comes to a complete standstill at the horizon. Simultaneously, due to extreme gravitational redshift, the wavelength of light emitted by the object is continuously stretched, from visible light through infrared and radio waves, until it becomes completely undetectable. This effect makes it appear to external observers that an object falling into a black hole requires an infinite amount of time to reach the event horizon. The situation is entirely different in the free-falling observer's frame of reference. Crossing the event horizon is a smooth process. No special physical phenomenon marks this moment. The observer experiences no shock or obstruction, nor does he perceive any visible boundary. He may have crossed this critical point unknowingly. This disparity in experience between internal and external observers embodies a core principle of general relativity. Different observers, based on their state of motion, will experience different spacetime. The radius of the event horizon is known as the Schwarzschild radius. This value depends solely on the black hole's mass. For a black hole with the mass of the Sun, the Schwarzschild radius is approximately 3 kilometers. For a black hole with the mass of Earth, the Schwarzschild radius is merely 9 millimeters. This simple mathematical relationship reveals a profound truth. Any object compressed to a size smaller than its Schwarzschild radius will inevitably become a black hole. The size and shape of the event horizon are also influenced by the black hole's rotation. For a rotating Kerr black hole, the event horizon flattens into an ellipsoid and is surrounded by a region called the ergosphere. Within this region, objects cannot remain stationary, but are dragged along by the black hole's rotation. This phenomenon, known as frame dragging, is a significant prediction of general relativity. The thermodynamic properties of the event horizon are equally thought-provoking. According to Hawking radiation theory, the event horizon is not an absolute black wall. Quantum effects allow particle pairs to form near the horizon, with one particle falling into the black hole, while the other escapes into the distance. This process causes black holes to actually emit radiation, and thus gradually lose mass. This implies black holes are not eternal entities. They possess extraordinarily long lifespans, but will ultimately evaporate and vanish through this quantum process. The event horizon also holds the mystery of the information paradox. According to classical general relativity, any information falling into a black hole is lost forever. This conflicts with quantum mechanics' unitarity principle. Contemporary theoretical physicists are striving to resolve this conundrum. New concepts like the holographic principle suggest That information falling into a black hole may be encoded on the surface of the event horizon. The event horizon is not a grave for information, but potentially a storage medium for it. On cosmological scales, the concept of the event horizon finds broader application. The universe itself possesses a similar event horizon, due to the accelerated expansion of the universe. Light emitted by distant galaxies may never reach us, forming a cosmological event horizon. These event horizons, differing in scale and nature, all speak to us of the same truth. Regions within the universe remain forever beyond our direct observation. The event horizon functions like a one-way door, permitting matter and information to enter from the outside, while barring anything from escaping within. This asymmetry profoundly shapes the interaction between black holes and the external cosmos, and molds our understanding of the universe's essence. Though we can never directly observe the interior beyond the event horizon, by studying the nature of this boundary itself, we gain glimpses into the deepest mysteries of spacetime. The event horizon is not merely the boundary of a black hole, but the frontier of our knowledge. Here, the laws of physics we know face their most severe tests. And here, we are most likely to discover the dawn of new physics. Crossing the event horizon is merely the first step in exploring the interior of a black hole. Beyond this invisible boundary awaits a world of even greater strangeness, a realm where human physics faces its ultimate test. Here, our familiar concepts of spacetime break down completely, and known physical laws gradually lose their validity. The structure of spacetime undergoes a fundamental transformation within the event horizon. In the external universe, time always flows forward, and the spatial dimensions allow us to move freely. We can choose to move forward or backward, left or right, up or down. But inside a black hole, this freedom vanishes. The roles of space and time undergo a startling reversal. The radial dimension, the direction toward the black hole's center, becomes the time-like dimension. This means that just as we cannot halt time's passage in the external universe, within a black hole, we cannot halt our motion toward the singularity. The temporal dimension, meanwhile, becomes a space-like dimension, where movement is theoretically possible, yet entirely devoid of the familiar meaning we associate with it. The immediate consequence of this role reversal is that all matter and radiation crossing the event horizon have their future light cones pointing directly toward the black hole's center. No space-time path can escape this region, not even if you travel at the speed of light. Even with infinite energy, you cannot alter this fate. This is not because some force tugs at you, but because space-time's very structure dictates it. Within a black hole, falling inward ceases to be a consequence of gravitational pull, and instead becomes the inevitable flow of time. Just as in the external universe, we cannot avoid moving toward the future. Within a black hole, we cannot avoid moving toward the singularity. As one plunges deeper toward the black hole's center, tidal forces begin to reveal their power. Tidal forces stem from the gradient of the gravitational field. That is, the rate at which gravity changes in space. On Earth, tidal forces manifest as the moon's gravitational pull stretching the oceans. Near a black hole, this effect is amplified to extreme levels. For a stellar mass black hole, tidal forces become exceptionally powerful near the event horizon. Any falling object will be stretched into a stream of atoms, before even reaching the event horizon. This process is called spaghettification, because the object is stretched vertically, while being compressed horizontally, much like spaghetti noodles. However, for supermassive black holes, the situation differs. Due to their extremely large Schwarzschild radii, the gravitational gradient at the event horizon is relatively gentle. An observer might experience no noticeable tidal forces while crossing the event horizon, but as they continue falling toward the center, the tidal forces gradually intensify and begin exerting significant effects on the falling object. This intensification is not linear, but increases dramatically as distance decreases. Inside the black hole, spacetime curvature increases infinitely as one approaches the center. This means the mathematical tools we use to describe physical phenomena begin to encounter severe problems. In general relativity, spacetime curvature is described by the Riemann tensor. When this quantity approaches infinity, our equations lose predictive power. This is known as the singularity problem. A singularity is not a point located in space, but a place where spacetime itself cannot extend further. It is the endpoint of causality, the boundary where all physical laws cease to apply. According to the predictions of general relativity, a true singularity exists inside a black hole. The fate of all matter falling in ends here. Mathematically, a singularity is defined as a point in spacetime that cannot be described by any coordinate system. There, the curvature scalar diverges to infinity, and density and temperature also become infinite. The emergence of these infinities is generally seen as a signal that the theory itself requires revision, indicating that general relativity, under such extreme conditions, is no longer applicable. For non-rotating Schwarzschild black holes, the singularity is predicted to be a point singularity, located at the very center of the black hole. All falling objects will reach this point within a finite proper time, from the faller's reference frame. This process may take only seconds or minutes, depending on the black hole's mass. For a rotating Kerr black hole, the situation is more complex. The singularity is predicted to be a ring-like structure. Theoretically, paths may exist through this ring, leading to other regions of spacetime, but these remain at the level of mathematical possibility. As one approaches the singularity, quantum effects begin to dominate. When the scale of spacetime curvature approaches the Planck scale, that is, 10 superscript 3 meters, quantum gravitational effects can no longer be neglected. At this scale, spacetime itself may no longer be smooth and continuous, but instead composed of discrete, spacetime atoms, or exhibit a foamy structure. Various theories of quantum gravity, such as string theory and loop quantum gravity, make differing predictions about spacetime behavior near the singularity. Some theories suggest that the singularity's infinities are smoothed out by quantum effects, and spacetime may bounce back, forming a white hole that ejects matter into another universe. This is known as the quantum bounce hypothesis. Other theories propose that singularities might be transitional regions, connecting our universe to others, or linking different parts of spacetime. Further theories suggest that no true singularity exists inside black holes, but rather a Planck star, a dense celestial body supported by quantum gravitational effects that prevents infinite collapse. Within black holes, information appears to face an ultimate fate. According to classical general relativity, all information falling into a black hole is completely annihilated at the singularity. This creates a sharp contradiction with the law of information conservation in quantum mechanics. This is the famous black hole information paradox. Modern physics is striving to resolve this conundrum. New concepts like the holographic principle suggest that information falling into a black hole may be encoded on the event horizon, or gradually released through Hawking radiation. The journey from event horizon to singularity, though potentially completed in an infinitesimal time span, it traverses a spectrum of physical phenomena, from macroscopic to microscopic, from classical to quantum. This journey challenges our most fundamental physical concepts, including causality, locality, and the very nature of spacetime itself. The interior of a black hole may serve as a gateway to multiverses, or as the cradle of new physics. Our current theoretical tools remain inadequate to fully describe this mysterious realm. Research into the internal structure of black holes drives the advancement of quantum gravity theory. Each theoretical breakthrough has the potential to transform our understanding of black hole interiors. Perhaps in the near future, through new discoveries in gravitational wave astronomy, or progress in quantum gravity theory, we may unveil the mysteries within black holes. For now, the interior of black holes remains at the frontier of human cognition, a realm both terrifying and captivating. Within this domain, we explore not only the mysteries of the cosmos, but also the very boundaries of physics itself. Every contemplation of a black hole's interior compels us to re-examine fundamental concepts we believed understood. Space, time, matter, energy within a black hole. These concepts manifest in ways utterly distinct from everyday experience. The interior of a black hole may be the loneliest place in the universe. Here, all connections to the external cosmos are severed. No information can be received, nor send any signals. Your only direction is toward the singularity. Your only time is the time of your fall. This absolute isolation, this irreversible fate, makes the interior of a black hole one of the most extreme environments in the universe. Yet even in such an extreme environment, the laws of physics still apply to some extent. Although general relativity breaks down at the singularity, in most regions inside a black hole, it still provides an accurate description. We can calculate the trajectories of falling objects, predict the evolution of tidal forces, describe the unfolding of spacetime curvature. Though these calculations cannot be experimentally verified, they are mathematically self-consistent and theoretically elegant. Understanding the interior of black holes also shapes our perception of the entire universe. If a singularity truly exists at the core, it signifies the complete breakdown of classical physics. If quantum effects could eliminate the singularity, then this implies the existence of theories beyond general relativity. Regardless of the scenario, research into the interior of black holes will profoundly transform our cosmic perspective. In this uncharted territory, every theoretical conjecture and every mathematical solution paints a map of the universe's deepest recesses. Though we may never directly verify these theories, through logical deduction and mathematical derivation, we can still glimpse a corner of this mysterious realm. The interior of a black hole represents not only gravity's ultimate triumph, but also the ultimate test of humanity's quest for knowledge. When we contemplate the interior of a black hole, we are fundamentally grappling with physics' ultimate questions. What is the nature of spacetime? Where does the universe originate? Where do the boundaries of physical laws lie? Within the black hole. These questions manifest in their most acute form, compelling us to continually expand the frontiers of our understanding. The interior of a black hole resembles a cosmic laboratory. Here, nature reveals itself in its most extreme form, exposing the deep structure of physical laws. Though this laboratory remains closed to direct observation, through theoretical research and mathematical exploration, we can still gain profound insights. These insights concern not only black holes themselves, but our understanding of the entire universe. The journey from the event horizon to the singularity may be the shortest voyage in the cosmos. It might take only minutes in time, and span mere hundreds of kilometers in space. Yet this brief journey embodies the entire transition from known physics to unknown physics. Here, classical concepts gradually fail. Quantum effects begin to dominate, and the structure of space-time undergoes fundamental change. This may be the most challenging and most enlightening journey in human physics. Though we cannot personally experience this journey through the tools of theoretical physics, we can complete this exploration in our imagination. Each such thought experiment deepens our understanding of natural laws and propels physics forward. The interior of a black hole, this seemingly unreachable realm, is in fact the cradle where new physics is born. Within the most extreme environment in this universe, in the deepest darkness, may lie the universe's most profound secrets, awaiting our discovery and comprehension. The interior of a black hole is not only a physics conundrum, but also a philosophical challenge, compelling us to contemplate. Black hole classification is based on their fundamental physical properties: mass, angular momentum, and charge. These three parameters entirely determine a black hole's external characteristics. This is the famous no-hair theorem. This implies that regardless of the material from which a black hole forms, it will ultimately evolve into a simple combination of these three properties. The simplest type of black hole is the Schwarzschild black hole, named after the German physicist Karl Schwarzschild. In 1916, he first arrived an exact solution to Einstein's field equations. A Schwarzschild black hole carries no charge and does not rotate. Its properties are determined solely by its mass. Its event horizon forms a perfect sphere. Its radius is directly proportional to its mass. For a black hole with the mass of the Sun, the Schwarzschild radius is approximately 3 kilometers. This implies that if the Sun were compressed into a sphere with a radius of 3 kilometers, it would become a black hole. The internal structure of a Schwarzschild black hole is relatively simple. From the event horizon to the central singularity, the curvature of spacetime increases steadily. Any object falling into it will reach the central singularity within a finite time. However, in the real universe, the vast majority of black holes rotate rapidly. This is the Kerr black hole. Its mathematical solution was discovered by New Zealand mathematician Roy Kerr in 1963. A rotating black hole possesses angular momentum. This significantly alters the space-time structure around the black hole. The event horizon of a Kerr black hole is no longer a perfect sphere. Instead, it bulges at the equator and flattens at the poles, forming a shape resembling a pumpkin. The most distinctive feature of a Kerr black hole is the existence of the ergosphere, located outside the event horizon. The ergosphere is a donut-shaped region. Within the ergosphere, spacetime itself is dragged by the black hole's rotation. This phenomenon is called frame dragging. Any object entering the ergosphere cannot remain stationary, even if moving at the speed of light. It will be swept along by the spacetime flow and forced to rotate. This effect is most pronounced in the black hole's equatorial plane. The existence of the ergosphere enables energy extraction from a rotating black hole. This is the famous Penrose process. When a particle enters the ergosphere and splits into two parts, one part may carry negative energy and fall into the black hole, while the other escapes with more energy than it originally possessed. This process effectively extracts energy from the black hole's rotation. Over time, it causes the black hole to gradually slow its rotation, until it eventually ceases to spin. The internal structure of a Kerr black hole is far more complex than that of a Schwarzschild black hole. Its singularity is not a point, but a ring-shaped structure. Theoretically, if one could bypass this annular singularity, it might be possible to traverse to other regions of spacetime. This provides a mathematical possibility for the existence of wormholes. However, such traversal may be impossible in practice, due to the intense gravitational field surrounding the annular singularity, and the tidal forces capable of tearing apart any traversing object. Charged black holes are described by the Reissler-Nordström solution. Such black holes carry electric charge in addition to mass. The presence of charge alters the structure of the event horizon. Charged black holes possess two horizons, an outer horizon and an inner horizon. Between these two horizons, the nature of time and space undergoes peculiar transformations. The radial coordinate becomes time-like, while the time coordinate becomes space-like. This implies that between the two horizons, objects cannot remain stationary, and must perpetually move inward or outward. The most general type of black hole is the Kerr-Newman black hole, which possesses both mass and angular momentum as well as electric charge. This black hole combines the characteristics of Kerr black holes and charged black holes, featuring energy shells and dual horizons. Its mathematical description is the most complex, but such black holes may be relatively rare in nature, as black holes typically acquire angular momentum through accretion, and this process often neutralizes their charge. Black holes span an enormous size range, from microscopic black holes to supermassive black holes, differing by more than 10 orders of magnitude in mass. Stellar mass black holes typically form from the collapse of massive stars, with masses ranging from 3 to 100 solar masses. These black holes are scattered throughout the Milky Way. Some reside in binary star systems, emitting X-ray radiation by accreting matter from companion stars. Intermediate mass black holes possess masses ranging from 100 to 100,000 solar masses. They may exist at the cores of globular clusters, or form through the merger of smaller black holes. These black holes serve as crucial links between stellar mass black holes and supermassive black holes, though their formation mechanisms remain an unsolved mystery. Supermassive black holes reside at the centers of galaxies, with masses ranging from millions to billions of solar masses. The Sagittarius A** black hole at the center of our Milky Way has a mass of approximately 4 million solar masses. The formation mechanisms of these giants remain incompletely understood. They may have formed through direct collapse in the early universe, or grown through the continuous merger and accretion of smaller black holes. Another key characteristic of black holes is their thermodynamic nature. While classical black holes emit no radiation, quantum effects cause them to slowly evaporate. Through Hawking radiation, the temperature of Hawking radiation is inversely proportional to the black hole's mass. For stellar mass black holes, the temperature of Hawking radiation is extremely low, and is completely drowned out by the cosmic microwave background radiation. Only primordial black holes with extremely small masses can potentially be detected through Hawking radiation. The entropy of a black hole is also a significant characteristic. Bekenstein and Hawking discovered that the entropy of a black hole is proportional to the area of its event horizon, rather than its volume. This suggests that black holes may follow the holographic principle. The information required to describe a region of space can be encoded on its boundary. Observational approaches. We can study black hole properties through multiple methods. For black holes in binary systems, we can precisely measure their mass by analyzing the motion of the companion star. By studying the inner edge of the accretion disk, we can infer the black hole's rotation speed. Charge, however, is harder to measure, because plasma in the universe rapidly neutralizes any net charge. Recent advances in gravitational wave astronomy have opened new windows for studying black hole properties. By analyzing gravitational wave signals emitted during black hole mergers, we can precisely measure the pre-merger masses and spins of the black holes, as well as the properties of the final merged black hole. These observational data are continually testing and refining our theoretical understanding of black holes. Research into black hole types and characteristics is not only about the black holes themselves, but is also closely linked to the advancement of fundamental physics. From the Noether theorem to Hawking radiation, from the area entropy formula to the holographic principle, every discovery about black hole properties is propelling our understanding of physics. Black holes are like fundamental particles in the universe, embodying the most profound physical laws. With their minimalistic characteristics, with the continuous advancement of observational technology, we are unveiling the veil of these most mysterious celestial bodies in the cosmos. Each new discovery enriches our knowledge of black hole types and characteristics. From the simplest Schwarzschild black hole to the most complex Kerr-Newman black hole, each type narrates a distinct story of spacetime and gravity. Together, these stories form our understanding of the most extreme celestial bodies in the universe. Though black holes themselves emit no light, astronomers have confirmed their existence through multiple indirect methods. This observational evidence forms the solid foundation of modern astrophysics. The first conclusive evidence came from X-ray binary systems. In these close binary systems, a black hole and an ordinary star orbit each other. When matter flows from the companion star toward the black hole, it forms a high-temperature accretion disk, emitting intense X-ray radiation. Cygnus X1 stands as the most famous example. This system contains a black hole approximately 21 times the mass of the Sun that draws matter from its supergiant companion star, producing detectable X-ray signals. At the center of the Milky Way, astronomers discovered direct evidence of a supermassive black hole. By tracking stellar motion, decades of observations using large telescopes, scientists precisely measured the orbits of stars near the galactic center. These stars revolve around an invisible point at astonishing speeds. Calculations reveal this unseen mass center possesses approximately 4 million times the mass of the Sun, concentrated within an extremely small spatial region. This strongly suggests the presence of a supermassive black hole at the center of the Milky Way, what we refer to as Sagittarius A star. Active galactic nuclei and quasars provide evidence for black holes in the distant universe. These brightest objects in the cosmos are actually powered by the accretion processes of supermassive black holes at the centers of galaxies. As vast amounts of matter fall toward the black hole, the accretion disk heats to extreme temperatures, releasing more radiation energy than the entire galaxy. By analyzing the spectral characteristics of this radiation, we can infer the central black hole's mass and accretion rate. The advent of gravitational wave astronomy has brought a revolutionary perspective to black hole research. When two black holes orbit each other and eventually merge, they generate ripples in spacetime, gravitational waves. The Laser Interferometer Gravitational Wave Observatory, LIGO, and the Virgo Interferometer have detected dozens of black hole mergers. These observations not only confirm the existence of black holes, but also provide key parameters like mass and spin, revealing a previously undetectable population of cosmic black holes. Black holes exert profound and complex influences on their host galaxies. The mass of a supermassive black hole at the galactic center is tightly correlated with the mass of the galactic bulge. This indicates coevolution between black holes and galaxies. This correlation implies the existence of a feedback mechanism. Through accretion and jet processes, black holes release immense energy into their surroundings, regulating galactic evolution. During active accretion, intense radiation and relativistic jets can heat galactic gas, inhibiting star formation. This negative feedback mechanism prevents excessive galactic growth, maintaining cosmic ecological balance. In certain scenarios, black hole jets can even expel gas entirely from the galaxy, permanently halting star formation activity. Conversely, black holes may also stimulate star formation. When jets collide with interstellar medium, the resulting shock waves compress gas clouds, triggering new star formation. This positive feedback mechanism, observed in some starburst galaxies, demonstrates the complexity of black hole influence on galactic evolution. On larger scales, black holes shape the formation of cosmic structures. Supermassive black holes in the early universe, through their rapid growth and intense radiation, may have reionized the cosmos, ending the so-called cosmic dark ages. These ancient black holes, like beacons in the cosmos, illuminate the evolutionary history of the early universe. Gravitational waves generated by black hole mergers provide a unique laboratory for testing general relativity. In strong gravitational fields, Einstein's theoretical predictions have been precisely validated. Predictions including gravitational wave emission and the no-hair theorem show remarkable agreement with observational data. Each detected black hole merger event constitutes a crucial test of fundamental physical theories. by studying populations of black holes across different mass scales. Astronomers are constructing a comprehensive evolutionary picture of black holes. From stellar mass black holes to intermediate mass black holes, and on to supermassive black holes. Each link in this mass sequence holds crucial information about cosmic evolution. The detection of intermediate mass black holes in particular will help us understand how the cosmic giants at the centers of galaxies grew from seed black holes. Future observational facilities will further enhance our capabilities to study black holes. The Event Horizon Telescope, EHT, continues to expand, aiming to capture clearer images of black hole shadows. The Laser Interferometer Space Antenna, LISA, will detect mergers of even more massive black holes. The James Webb Space Telescope is investigating black holes in the early universe. These observations will collectively advance our understanding of black holes and their cosmic impact. Black holes are not merely peculiar celestial bodies in the cosmos, but also crucial drivers of cosmic evolution. Through accretion and feedback processes, they shape the structure and fate of galaxies. Via gravitational wave radiation, they alter the dynamical evolution of binary systems. As laboratories of extreme physics, they test the boundaries of fundamental physical theories. From minuscule primordial black holes to the behemoths at galactic centers, each black hole plays a unique and vital role in cosmic evolution. They are both destroyers of the cosmos and creators of new worlds, both the end of space-time and the beginning of new discoveries. On the path to exploring black holes, we have not only uncovered cosmic mysteries, but also gained deeper insights into the essence of physical laws. With the continuous advancement of observational technology, we believe more secrets of black holes will be revealed, including how they form, how they evolve, and how they influence the distribution of matter and energy on cosmic scales. Each new discovery rewrites our understanding of the cosmos, propelling humanity's comprehension of nature toward new heights. Our journey nears its conclusion. From the mysteries of space-time curvature to the grandeur of stellar collapse. From the irreversibility of the event horizon to the unknown of the singularity. We have traversed the frontiers of human cognition, exploring the most extreme realms of the universe. Now let these grand concepts slowly settle, like starlight traversing the vast cosmos to arrive gently at its destination. The silence of a black hole is not emptiness but fulfillment. Not an end but another form of existence. Like a mind preparing for sleep, no longer clinging to the clamor and distractions of the day, naturally sinking into the vastness within. Now feel the points where your body meets its support. Perhaps the contact between your back and the bed, or your arms resting against the armrests. Use these sensations as anchors to ground yourself in the present moment. Let your breath return to its natural rhythm. No need to control or adjust. Simply observe the breath flowing in and out like tides. Know you are inhaling as you breathe in. Know you are exhaling as you breathe out. Each exhalation is a release. Release today's fatigue. Release the burdens of thought. Release the clinging to knowledge. Release the anxiety about the unknown. Imagine yourself floating in boundless space, surrounded by warm, profound darkness. Distant galaxies swirl like gauze, their motion so slow, so serene, as if the entire universe prepares for sleep. At this scale, All worries seem insignificant. All attachments lose their importance. Black holes teach us the wisdom of letting go. They resist not, cling not, but simply exist naturally, accepting all matter and energy that falls within, yet grasping nothing tightly. Now let us learn this wisdom. Release the memories of the past. Release the worries of the future. And simply exist in this present moment. Feel the weight settling over your eyelids. If they wish to close, let them close naturally. If they still wish to open, do not force them. Let every part of your body find its most comfortable state. Toes relax. Fingers relax. Facial muscles relax. Shoulders relax. Just as matter moves naturally along geodesics, within a black hole's gravitational field, allow your body to follow gravity's guidance, surrendering completely to the force that supports you. Within the event horizon of a black hole, all arrows of time point toward the center. All paths lead to the singularity. Now let your thoughts find this singular direction. No longer wandering aimlessly, no longer wavering. Simply pointing toward rest, toward tranquility, toward the depths of slumber. Black holes in the cosmos wait in silence. They have existed for billions of years, and will endure for far longer. Their patience transcends human comprehension. Now let us cultivate such patience. No rushing to sleep, no forcing relaxation. Simply allowing everything to unfold naturally. Just as matter naturally falls into a black hole. Just as galaxies naturally rotate. Perhaps in some distant galaxy, a black hole quietly absorbs matter, emitting a faint glow. Perhaps at the center of our Milky Way, Sagittarius A** slowly rotates, guarding the galaxy's secrets. These cosmic rhythms are so vast, yet so serene. Now let this serenity flow into your consciousness, replacing all thoughts and distractions. Your breath grows steadily calmer. Your heartbeat grows slower. Your body grows heavier. Just as a star at the end of its life naturally collapses into a black hole, let your conscious mind naturally collapse into the event horizon of sleep. Within this boundary, logic yields to intuition, thought yields to feeling, wakefulness yields to dreams. Outside, the universe continues to expand, galaxies continue to spin, black holes continue to wait. But all of this can now be set aside, like matter crossing the event horizon, no longer needing to concern itself with the affairs of the external universe. All you need to do now is rest. Let consciousness sink into dreamless slumber, or drift toward fantastical dreams. Science tells us black holes are gravity's ultimate triumph, and sleep at this moment is essential nourishment for health. Let us gladly accept this natural gift, without resistance or struggle, trusting completely in the body's wisdom. It will guide you into the rest you need. In the distant future, when humanity may traverse the stars, when technology may unlock all black hole mysteries, explorers of that era will still need, just as we do now, to lay down all seeking at day's end, to enter restorative sleep. This is the shared rhythm of cosmic life. Now night deepens, starlight fades. Let your final conscious breath carry you across the threshold of wakefulness and sleep, like matter crossing the event horizon, calmly, naturally, irreversibly, entering that realm where all paths lead to rest. Good night, dear explorer. May you find the deepest peace in the embrace of the cosmos. May your dreams be as brilliant as galaxies, or as serene as black holes. In this boundless universe, your rest is as vital as your exploration, equally precious.